Welcome to this explainer. Today we're diving into something that sounds deceptively simple, a single new HTTP method called query. But here's why it matters. For over 3 decades, every developer building a complex search API, every GraphQL endpoint, every Elasticsearch-backed application has been forced into the same ugly compromise. Send read-only data in the body of a POST request, a method designed for creating resources and triggering state changes, repurposed for something that should have been safe, cacheable, and retryable from day one. On June 19, 2026, the Internet Engineering Task Force published RFC 10008, a proposed standard that adds exactly one word to the HTTP vocabulary: queries. And that single word could fundamentally reshape how the web handles complex data retrieval. Let's kick things off with Section 1, why GET fails for complex queries. And to understand this, we need to look at the HTTP specification itself. RFC 9110, the current HTTP semantics document, defines GET as safe, idempotent, and cacheable. That's the holy trinity of HTTP methods. Safe means it doesn't change server state. Idempotent means you can send it multiple times and get the same result. Cacheable means intermediaries can store and serve the response. But here's the catch. GET carries its data exclusively in the URI, that query string you see after the question mark. Every filter, every sort parameter, every search term. It all lives in the URL, and the HTTP specification, RFC 9110, Section 4.1, explicitly says that servers and intermediaries should support request targets of at least 8,000 octets, 8,000 characters. That's the recommended minimum. Now, 8,000 characters sounds generous until you try to encode a complex JSON filter object into a URL. Every brace, every bracket, every colon needs to be percent encoded. A modest 50-line filter expression balloons into a multi-kilobyte URI. And here's the real problem. RFC 9110 says should support 8,000 octets, not must. Your request passes through a proxy, a load balancer, a CDN edge node, and a WAF, each of which has its own internal URI length limit. You don't know the real limit of the path your request takes until you hit it. This is not a theoretical problem. Research from the HTTP-BIS working group documented production failures where URIs were silently truncated by intermediaries without any error response reaching the client. The data was simply lost mid-flight, and the server processed an incomplete query. The second problem is logging. Every component in that chain logs the full URI. Your search query, potentially containing sensitive filter parameters, user identifiers, or business logic, ends up in server access logs, proxy logs, CDN logs, and if you're not careful, browser history and bookmark files. Julian Reschke, one of the RFC's authors and co-editor of the HTTP 1.1 specifications, has been raising this concern in IETF discussions since at least 2014. And the third problem, the one that matters most to architects, is that GET violates REST's resource-oriented model when used for complex queries. In REST, every URI identifies a resource. But when your query parameters change, you're effectively creating a new resource identifier for every unique combination of filters. The URI is supposed to identify the resource, not encode the query. These 3 problems, unpredictable URI limits, sensitive data in logs, and REST model breakage, are the exact motivation the RFC authors cite in Section 1 of RFC 1008. Let that sink in. For 30 years, the foundational retrieval method of the web has had these 3 known, documented, unsolvable within the spec limitations. Moving into Section 2, the POST workaround. Developers didn't wait for the IETF to fix this. The practical solution, used by virtually every complex API on the internet, is to send the query in the body of a POST request. GraphQL does this. Every single query, no matter how simple, goes through POST. Elasticsearch's Search API uses POST. The Wikimedia REST API uses POST for search. Microsoft's OData protocol, gRPC transcoded to HTTP, SOAP, all of them route read operations through a method that the HTTP specification explicitly marks as neither safe nor idempotent by default. And this is where the problem compounds. To any HTTP intermediary, a cache, a reverse proxy, a CDN, a POST request could be doing anything. It could be creating a resource. It could be processing a payment. It could be deleting data. The intermediary cannot assume it's safe, because the POST method carries no such guarantee. This means three concrete things. First, no caching. RFC 9110 section 9.3.3 says that responses to POST are only cacheable if they include explicit freshness information and a content location header. But even then, caches use the URI as the primary cache key, and every post to the same endpoint has the same URI, even with different bodies. The cache infrastructure simply wasn't built for this. Second, no automatic retries. If a GET request fails due to a network interruption, any HTTP client library can safely retry it. The spec guarantees it's safe and idempotent. But a POST? The client has to assume it might have created a resource, charged a credit card, or triggered a side effect. It cannot retry without understanding the application semantics. Third, ambiguous security posture. Web application firewalls and rate limiters treat POST differently from GET. They apply different rules, different rate limits, different inspection policies. A read-only operation routed through POST gets the same security treatment as a resource creation or a state mutation. The irony is stark. Developers chose POST because GET couldn't carry the data they needed. But by doing so, they sacrificed everything that makes GET valuable: safety guarantees, idempotency guarantees, and the entire caching infrastructure of the web. Which brings us to Section 3, the historical precedent. Because the idea of a safe HTTP method with a request body is not new. It predates RFC 10008 by more than 2 decades. In 2003, the IETF published RFC 5323, the WebDAV search method. WebDAV, or Web Distributed Authoring and Versioning, was an extension to HTTP for collaborative document management, and it needed a way to search across document properties. The search method did exactly what Query does today. It sent a query in the request body and returned results, with safe and idempotent semantics. But search was inextricably tied to WebDAV's resource property model. It wasn't designed as a general-purpose query mechanism for the broader web. In fact, early drafts of what became RFC 10008 actually used the name search before the HTTP BIS working group deliberately renamed it to question. The appendix of RFC 10008 explicitly documents this decision. The authors wanted to avoid any semantic association with WebDAV and instead emphasize the connection to a URI's query component, the part after the question mark. Query generalizes that concept to any resource type and any query format. What's notable is that Julian Reschke, who co-edited the WebDAV search specification in 2003, is also a co-author of RFC 10008. The lineage is direct. The web has needed this for 23 years, and the same people who built the predecessor are now building the standardized solution. Moving into Section 4, the core of the specification. What exactly is the query method? At its simplest, query is what POST should have been for read operations. It sends the query content in the request body, just like POST, but it carries explicit safety and idempotency guarantees, just like GET. One word changes everything. A proxy, cache, or load balancer knows about the request. Here is the comparison directly from the RFC. Get is safe, idempotent, and cacheable, but has no defined semantics for a request body. Query is safe, idempotent, and cacheable, and expects a body. Post is neither safe nor idempotent by default, and can only be cached for subsequent GET requests. But question is not just post with a different name. The RFC defines several specific behaviors that distinguish it. First, content type is mandatory. Unlike post, where a missing content type might be tolerated, a query's request without a content type header must be rejected with a 400 bad request. The server cannot guess what format the query is in. If the server receives a content type it doesn't support, it responds with 415, unsupported media type. And here's an elegant detail. The server can include an accept query header in its response, listing the content types it does accept. This allows clients to discover supported query formats without out-of-band documentation. The RFC also defines a 422 unprenomizing content status code for cases where the query is syntactically valid but semantically broken. For example, referencing a table or field that doesn't exist. And 406, not acceptable, when the server can't produce the response format the client requested. Now here's where it gets particularly interesting. The RFC introduces the concept of an equivalent resource. When you send query to a resource with a body, the server conceptually derives a new resource, the equivalent resource, that represents the result of that specific query. This equivalent resource is what would respond to a GET request. Servers can optionally assign URIs to equivalent resources, making queries bookmarkable and shareable. This is done through two separate headers. Content location points to the specific results of this query. A temporary resource you can get to retrieve those exact results. Location points to the equivalent resource itself. Send a GET to this URI, and you'll repeat the query without needing to resend the body. This distinction is subtle but powerful. Content location is for result caching. Location is for making queries first-class resources that can be shared, bookmarked, and navigated to directly. This is something that's simply not possible with post-based queries today. The caching behavior is where Quick Queries delivers its biggest practical win. Cache keys for query responses must incorporate the full request body and associated metadata. Unlike Post, where the URI alone is insufficient as a cache key, a question cache key captures everything that makes the request unique. And there's an important detail. Caches are allowed to normalize the body for key generation purposes. They can strip content encoding, normalize JSON whitespace, reorder fields, but only for computing the cache key, never for modifying the actual request forwarded to the origin server. Conditional requests work the same as GET. If none match, if modified since, if match, if unmodified since, all fully supported. Range requests for partial results, also supported. These are not afterthoughts. They are first-class features because Query inherits them from the HTTP caching model that GET has used for decades. Redirection behavior is carefully specified. 301, 302, 307, and 308 redirects. The client repeats the query to the new URI. Unlike the GET exception for 301 and 302 where the method can change, question never gets downgraded to GET on redirect. A 303 redirect, however, tells the client to switch to GET. This is the mechanism for materializing a query result as a standalone resource. Moving into Section 5, Security Considerations. And I want to be absolutely clear. This is not a section filled with hypotheticals. The RFC itself devotes substantial space to security analysis, and independent researchers have already published attack surface assessments. The first and most critical risk is cache poisoning. RFC 10008 requires cache keys to incorporate the full request body. But what if a shared cache, operated by a CDN or a corporate proxy, only keys on the URI? If an attacker can send a query request that the cache stores under just the URI, every subsequent user sending query to that same URI receives the attacker's cached response. This is not a theoretical vulnerability. The RFC authors explicitly acknowledge it. The second risk is Web Application Firewall and Intrusion Detection System blind spots. Security policies for WAFs are typically written around get, post, put, delete, and patch. Query is a new method. If a WAF doesn't recognize it, query requests pass through uninspected, or worse, they're rejected entirely. Rails Action Pack framework currently rejects query requests before they reach the controller. This is a deliberate default. If the framework doesn't know what query is, it refuses to handle it. The third risk is cross-site request forgery. CSRF protections in web frameworks scope their checks to state-changing methods: post, put, delete, patch. Questory is defined as safe, so it would be exempt from CSRF token validation by default. If a developer builds a query endpoint that unintentionally has a side effect, that side effect gets a free pass through CSRF protection. The fourth consideration is CORS preflight. The RFC authors made a deliberate decision here. Query is not a CORS safe-listed method. Browsers cannot send query requests cross-origin without first triggering an options preflight. The working group decided that the security boundary should be explicit. Finally, there's the request smuggling vector. When a front-end proxy and a back-end origin server disagree about how to parse a questy query request, the content length versus transfer OK discrepancy that has plagued HTTP for years, classic request smuggling becomes possible. Moving into Section 6, the implementation landscape. RFC 10008 was published on June 19, 2026. As of July 2026, where does query actually work? Let's start with what's available today. No browser implements question natively. The Fetch API and experiment transport Prefetched don't recognize it. This means that for browser-based applications, query is not yet usable without a polyfill or a server-side proxy. On the server side, the picture is uneven but progressing. Node.js added support for queries in its HTTP module during the draft phase. Developers can use http.request with the method set to query today. Go's net/http package supports any custom method, including query, through HTTP degraded. No standard library changes are needed. But here's the crucial distinction. Server-to-server communication, where you control both ends of the connection, can use query today. If your backend services communicate over HTTP, you can deploy query between them immediately. The browsers are the bottleneck, not the servers. The CDN and proxy landscape is equally important. Cloudflare's James Snell and Akamai's Mike Bishop are RFC authors, which signals strong industry interest. But as of publication, no major CDN has announced production query support. This is the critical missing piece. Without CDN caching support, one of QUERY's, which brings us to Section 7, when not to use question. Because for all its advantages, query is not always the right choice. If your query fits comfortably in a URI, if it's under 1,000 characters and contains nothing sensitive, use GET. GET works everywhere today. It's supported by every browser, every cache, every CDN, every framework. If your application relies heavily on CDN caching and the CDN doesn't support QUERY.It, you're better off with POST. And if your query has side effects, if it updates a last access timestamp, increments a counter, or writes to an audit log, it is not safe, and it should not use question. Use POST. The safety guarantee of query is not optional. It's the entire point. The HTTP query method is, in many ways, a fix for a problem that never should have existed. GET was designed for simple resource retrieval in a web of documents. When the web evolved into an application platform with complex search APIs, structured query languages, and rich filtering, GET couldn't keep up. Developers adapted by using POST, and for 30 years that worked, at the cost of caching, retry safety, and semantic clarity. RFC 10008 doesn't introduce a revolutionary new capability. It standardizes what the industry has needed since the beginning: a safe, idempotent, cacheable method for complex data retrieval. One word: query. Thanks for joining me on this explainer. Keep building, and I'll catch you next time.